All right, let's do the third part of this problem. Here we'll actually use the numbers and we'll compute it. So actually I'll compute it sort of the typical way with the numbers. I need to get the numbers. I don't have my book open. But if you, I could plug it right into these design equations, but we basically implemented those in the program, so that'll be a check of that. But let's do instead, let's do it by hand, kind of in a more conventional way, if you were given numbers. And that way, the reason I like that is it gives you a second check. It gives you a check sort of on the derivation of your equations. I guess what I'm saying is, if there's an error in the way I derive the equations, and I use the same equations to compute the transverse shear with the numbers, right? It'll have those errors in it. Whereas if I do it with a different approach, like our general approach, well, an error in the equations or the implementation of the equations will be picked up. So it's a good trick for debugging, all right? So it's going to be the same problem, except we're going to use L equal to 4. This is all millimeter meter stuff. A is 2 meters. D1 is 0. D2 is going to be 2 meters. So actually P is going to be right at that point there. P is going to equal 1.5 kilonewtons. W is 400 newtons per meter. And just the T's. H is 150 millimeters. B is going to be 50 millimeters. That's B. T1 is 15 millimeters, and then T2 is 20 millimeters. Okay? So those are the values we're going to use. All right. So actually you can see, really, if I were to redraw the diagram, we don't need these, because this is what we use for our program. If I kind of redraw the picture, you'll see that P is right at the end of this point. So actually, this is the loading. We have the distributed force starts right at the end, goes to the midway point, and then the point load P is right at that same end point, okay? 1.5 kilonewtons, and this is 400 newtons per meter. This distance here is 2 meters, and this total distance here is the 4 meters, okay? And we still need to get the reaction at A and then the reaction at B. All right? All right. So this one has an effective down force of 800 newtons. That's the 400 newton meters over 2 meters, and its location is going to be 1 meter from the edge, right? So we can treat it like this to do the equilibrium for the whole body, to get the reaction forces. Right? And RA plus RB equals the 800 plus the 1500. So that's 800 plus 1500. So that's equal to 2300 newtons, okay? Now let's do sum of moments. We can do sum of moments around A. Let's do sum of moments around this point. Sum of moments around point A, so the RA doesn't enter into it. And then that's going to be a positive moment. So That gives me a minus 800 newtons times 1. That's in Newton meters. This is also a negative. That's a negative 1500. Its moment arm is 2, and that's going to be Newton meters. And then plus RB times its moment arm, which is 4. And that's going to have units of meters. And that has to equilibrate to 0. So from that we can get RB is equal to 800 plus 1500, which you already know is the 2300. Oops, I'm sorry, 1500 times 2 divided by 4. And that'll give me a result in newtons. And so that equals 3,800. 4 divide. It gives me 950 newtons. Okay, this is 950 newtons. And then RA from here is going to be 2,300 minus that, which is 1,350 newtons. Okay? So those are the reaction forces. Now we can do the shear diagrams, right? We only need to do the shear diagrams because we're not really interested. This problem is only asking for the transverse shear. All right, so let's look at the shear diagram. Let's first look at it from point A to the mid span, right? Call this point C. So from X, from 0 to 2 meters, what's the picture we have? Okay, this distance here is X. Here is the positive sense for the bending moment, which I actually don't care about, and that's the positive sense for the shear. We have upwards 1,350, and then we just have the downward effect of the distributed load. So it's going to have a value of 400 times x, right? Because it's 400 newtons per meter over x meters. And this distance here, well, let's use this distance, is going to be x on 2. That's the moment arm. We'll take the moments around that point, okay? So now if we do sum of forces, well, actually I can just do sum of forces. I don't need to do sum to do moments, right? Sum of forces in the y direction equals 0. That gives me minus the shear plus 1,350 minus 400x equals 0, or v of x equals 1,350 minus 400x. Okay? So if I were to draw that, here's x. I'm sorry, here's the midpoint. This is the point A, this is point B, and this is the shear diagram. So we start off at $1,350, and then we start to drop down at a slope of minus 400. So when we put in 2 here, right at the point 2, we get 800, so that's 1,350 minus 800. So this will drop down to a value of 550 here, right? So we get a straight line response. The slope here is minus 400 until we get right to the midpoint, and then the shear here should be 550, okay? Now we got to drop because of this one, and then it'll go straight over to 950 is what it should be, right? But we can look at that. If you want to look at the left section, this will get us from 2 to 4 meters. The only thing we have acting up is the 950 newtons. Now in this case, it's a negative phase, so the positive sense for the internal shear is up. And so this tells me, from sum of forces, that v of x equals negative 950. So actually that's what you would expect. So down here we'll be at negative 950. And it's going to have a constant value. So it's going to drop down like this, constant value, and then it jumps up here. And this delta is going to be 1.5 kilonewtons. Right, 1.5 kilonewtons. That's the jump value. So here is, in this particular case, the shear diagram, right? So that tells me that the maximum value, the maximum absolute value of shear is right here. So the Vmax is going to be the 1350 newtons. That's the one we're going to design to. So point A is the critical location. That's where it'll fail first in transverse shear, right? That's where you'll have the maximum transverse shear. Okay, now we need to compute the I and the Q's, all right? So first we need to get I of the entire cross section, right? So we'll have this we'll call like section 1, and this I'll call section 2. All right. So the area of 1 is going to be, we can do this, keep that there, right? So the area of section 1 is going to be 0.02 meters times its height, which is 0.15 meters minus 2 times 15 meters, or that's 0.03 meters. And that's going to equal .0024 meters squared. Okay. The area of the second section is going to be its base, which is 0.05 meters, 50 millimeters, times the height, which is 0.015 meters. And that's 0.00075 meters squared. Those are the areas. We need those to get the Q's, right? The I of the web, I of section 1, is going to be 1/12 the base, which is 0.02, times the height, which is going to be this value. Let me just write this value. That value is the 150 minus 0.03. So this is actually this distance here. This is 120 millimeters, right? That's 120 millimeters. So that's the height of the flange, 0.12 cubed. So that gives me 2.88 times 10 to the minus 6 meters to the 4th. The I of the flange is going to be its base, which is 0.05, wait, base is 0.5 meter. No, it's 50 millimeters. So it's 0.05, that's the base. Its height is the 0.15 cubed over 12. And then we have to shift by parallel axis. So it's its area, which is 0.00075 meters, times the distance to its centroid, which is going to be 1.15 divided by 2, that's this distance, minus 0.015 divided by 2, half the height, and that's squared. So that then becomes 0.05 0.015, 12 divided 0.1237, enter 0.15, minus, so this is 0.0675, square that, add those two together, and this becomes 3.70 times 10 to the minus 6 meters to the fourth. So the total I is I of the web plus 2 flanges, because we have 2 flanges. So that equals 10.3 times 10 to the minus 6 meters to the fourth. Okay, so that's the I. Now we need to get the Q. The Q we're interested in is the Q that gives us the maximum transverse shear. So that's the half of the beam. So to get the Q, I'll get another piece of paper, I guess. Shift it over here. All right. So to get the Q, that's going to equal the area of section 1 times its centroidal distance, which is going to be the 120 divided by 4. It's 0.12 divided by 4, right? That's the y. That's the distance from the neutral axis to its centroid, plus the area of the web, that one, and its distance from the neutral axis to its centroid is what we had before. That's the 60 millimeters plus half this height, which is half the flange height, which is 0.075. Okay, so that's going to equal area 1. Here we put in, let's just do it this way. This is going to be the 0.0024, and this one's going to be the 0.00075. And then when we do that, that gives us a value of this should actually be 0.0075, right? Another 0 here. So this Q becomes 0.123 times 10 to the minus 3rd meters cubed. Okay? All right, so now we know those things. I can now get the transverse shear. So the transverse shear, tau, is the V, that's the maximum, times the Q over the I times the thickness. Now we're getting the Q here, so the thickness is going to equal the thickness of that flange. That's going to be 0.5, right? No, what am I talking about? That's from another problem. It's the 20 millimeters. This is 0.02 meters, right? That's the T2. That's T2. So this now becomes the maximum V we got, 1350. The Q, which is 0.123 times 10 to the minus 3rd meters cubed, over the I, which is the 10.3 times 10 to the minus 6th meters to the 4th, times the thickness, which is 0.02 meters. And this will give us pascals. And the answer is 0.81 megapascals. That's the answer, okay? That's the maximum shear. It's at point A. At the neutral axis at point A, okay? All right, so now let's see, how this works out with our program. So here's the program we did before. Now I just kind of skipped a little bit behind the screen, so to speak, and I put in the values for the variables. And then when we go through, we evaluate everything, we go look at the answer, and of course, lo and behold, the answers do not match, right? So here I have actually 0.6 megapascals, and when I did it by hand, I got 0.8 megapascals. All right, so this is typical, maybe one thing you can get from me doing these videos is that I've been doing this for a long time and I always make mistakes. So I imagine most people watching these videos have not been doing it as long as I have and probably will make this as many, if not maybe more mistakes. Now, when you make a mistake, what do you do? Well, the trick is not to just give up and then fudge the answer. The nice thing about using computational tools like Mathematica is it's pretty easy to see where your mistake is. So the final answer is wrong, right? This tau max is wrong. We got an inconsistency. Here I'm saying I have, let's make this a little smaller. I don't think I really need this wide of a notebook. Here I'm saying the answer is 0.8, and here I got 0.6. Okay, well let's check some of the major components. Let's first check the Vmax. Do I get the same Vmax? When I did it by hand here, I got a Vmax of 1350. And I can actually check the V at A and the V at B. So I know the V at B is negative 950 and the V at A is 1350. So let's check both those values. Granted, I don't use the V at point B in this problem because that turned out to be less than V at A. But you should check that it's still the same because there might be another problem where actually the B will be the critical one. And if I have an error in that equation, then it'll be wrong. But if we look, you can see actually we get the V at A and the V at B correct. We pick the max one. So this all seems to work. So I really wouldn't spend too much time looking at all this stuff where I compute the reaction forces and then the V's, okay? Because that gives me the same answer that I got by hand. All right, so then the next one that we suspect is the computation of I and Q. Pretty sure T2 is the thickness, so that's right, unless I inputted it incorrectly. So it's the issue is looking at I and Q. Those are very suspicious because they're kind of tedious and they always give me a headache. All right, so when we look at this, I got for I, when I did it by hand, 10.3 times 10 to the minus 6th. So what did I get from I here? Well, it's a little off, but it's close. Okay? Instead of 10, it's 9.7. So that's close. I don't think that would be enough to make the difference, the 20% error that I've got. If I look at Q, now when I did Q by hand, I got a Q of 0.123 times 10 to the minus third, right? It's right over here. But here you can see the Q at line 56, out 56. Oh, there's a cursor on it. It's quite a bit different. So I definitely have an error in the computation of Q. So let's kind of double check that stuff. It actually might be my equations. let's kind of go in here. Let's compute Q a little differently. Let's see if we can get a confirmation of one of the numbers. So let's compute Q in Mathematica, kind of in the similar way that I computed Q here. All right, we can go through almost number by number and check everything. So I'm going to just start right here. So let's define A1. A1 is going to be the area of that's T2 times, well, I'm even going to define another variable. I'm going to define this 120 flange height, because that pops up all the time. So I'm going to call that H of the web. Okay, HW. All right. So let's define that parameter. HW is going to be the total height minus 2 times the thickness of the flanges, which is T1. Okay, T1. And so that gives me 120. That's what I expected. The area of cross-section 1 should be T2 times the height of the web. And is that confirm what I got? Okay, that matches with what I have here. Now let's go through and get A2. A2, whoops, what happened here? Oh, I'm in let's make another one. A2 is going to be the thickness of the flange, T1, times the base. Okay, so that's 0.075. That's correct. All right. Now, the I for section 1. Let's do I for 1. I think I probably already have that variable defined, so I probably should. Well, we'll redefine it. That's fine. I might, if this works out, I might just delete all that other stuff. Because I have a suspicion. I think when I did some of the algebraic simplification here, I think I might have screwed up. So I1 is going to be, whoops, 1/12 the base, which is T2, times the height. The height, now I got this web, so I know the height is going to be the height of the web, and that has to be cubed. All right, over 12. That's around the centroid, so that's what it is. 2.88, okay, that confirms that. All right. Now we're going to do I for section 2. Now that's going to be the same type of equation, but it's not T1. The base is B, and then the height is going to be T1. So that gives me the 1.4. Well, I guess that's what I have here, but then we have to add the parallel axis part to it. So that's going to be A2 times the distance, which is the height of the web, right? That's the distance from here to here, plus half of the flange thickness, T1 on 2. And then we have to square that, right? Whoops. All right, so let's see what I get here. This gives me I think I did something wrong here. You see, I got a different number for I2 than what I got here. All right, but I'm pretty sure this is right. And so now let's see what we get if we do I total. The I about the z-axis. Well, this equation still works, right? This still works. Let's just reevaluate it. And now I get to 0.02. So this actually is very close to this number. So this equation I suspect is right. I think I just made a mistake and actually the hand calc, okay? So the hand calc actually, I have a little error here. And I think the equation's right. I think it was just when I put everything into my calculator, I probably screwed up. Maybe it was this is wrong, okay? All right. So actually the I looks good, and this equation looks good. It seems to confirm. So you know what? I really don't need this stuff. But if you like it this way, I guess we can leave it this way. Actually, it's kind of something about it. I do kind of like actually the having all the parameters kind of computed more directly, as in this format, than deriving equations. Because deriving equations sometimes can be erroneous. The power of the computer is that you can kind of go through and actually. Oops, I don't need this. Right? You don't need to have these equations. You can actually compute things sort of sequentially. Right? Now I don't really need this Q. I don't need any of this stuff. I can get rid of this. All right, I don't need these obviously. These are just the valuations. Now the Q is a little off as well. Let's just double check the Q. The Q is close, but not quite right. So let's do Q kind of in a direct manner as well. So Q, the Q for section 1, well, let's do it down here. I need to do it down here. The Q for section 1 is going to be the area for section 1, but that's the flange, so that's the total area. Oh, you know, I needed to divide this by 2. That was the mistake. Okay, now I see the mistake. Right? The Q I needed for this area for the first section is half of the area 1. And I didn't put that up here. I didn't put that in here. I used the 0.024. This really needed to be 0.024 divided by 2. Okay? Oops, you can't see that. Right, this was the error. I didn't have the area should be over 2. I didn't have that, okay? So that's what I needed to do. I bet you that's the mistake. Okay? So, I suspect that this actually is right. This Q is actually right. Okay, so why do we want to fix that? So this is area 1 divided by 2 times its centroidal distance, which is going to be the web height divided by 4, right? So that's Q1. That came out to be the same as that equation, so that seems right. Then we can add Q2. Q2 is going to equal area 2. It's the full area times its distance, which is this. That's the centroidal distance, right? And that's the 0.00925. Which is a little different than what I got here. I'm not sure, but I'm pretty sure this is right. See, I think I'm getting multiple mistakes. I forgot about this one, but this one might be. Yeah, this is the 1/2 on that. Huh, that should be the same. I'm surprised that's not the same. Area 2. This is area 2, base times T1. Right? Area 2 is base times T1. And then this is the centroidal distance. The web height plus half of the flange, which should be the same as half of the height minus half of the thickness. Huh. That's weird. I'm not sure what's going on there. So h times t1. So the area's got to be the same, right? Am I making a logic error in this? This is the flange height. Half of that. Ah, this should be half, right? This has to be half of the flange, that height, right? This is this. Now watch. Now I get the same value. Now I see that Q2 is the same. So this checks. I've computed it kind of two different ways, and I get the same answer. Actually, I think I like the direct approach a little better than the equation approach, right? The equation approach looks nice, makes a nice equation you can put in a book, but actually, I think I have a little more confidence in doing the direct computations, right? Let's put all these into one section. I'm just cleaning it up a little bit. Actually, let's put all these into its own. I shouldn't really do this in here because you guys don't care about this stuff. I'm just to get a little nuts about making sure things are neat. I don't need any of these. And then this, I can just get a return. Okay, so now we kind of compute the area properties, we compute the i's, and we compute the q's. All right, so we can do this. That doesn't really do me anything. This puts out the I, and this puts out the q. And now we can go through and I think we can get the right answer now. I should double check everything again, but I think I found most of the mistakes. I found some mistakes in my hand calculations and some mistakes in my computation. Let's evaluate the notebook. I don't know why it always makes a double evaluation of the picture. That doesn't really do me any good. And so here we have the Q's and I's that match our hand calculation, I believe. Well, we had an error in this I, right? I think we have the correct I's and the correct Q's. We already have confidence in our shear forces, and so this actually tells me that actually the max shear stress should be 0.2 megapascals or 214 kilopascals. Okay. All right. Well, it took a lot of effort, but for doing one problem, maybe doing the Mathematica stuff might be a little overkill. But if you really want to be able to do a problem with high confidence, like when I work with teams that are working on design projects and their calculations have to be correct, or obviously when you're in industry, when you really want to have correct calculations, there's a big advantage of using this stuff over using the hand calculations, because you can see finding the errors in the hand calculations can be a little tedious. Here, you can really kind of easily go through stuff step by step and find the errors. You can see I used the Mathematica routine to kind of do the what ifs and find the errors, not the hand calculations, because it was just a lot easier. Okay, well I hope this one helped, and I hope that people kind of have see the benefits of using one of these programs. Now, if you don't have access to Mathematica, and Mathematica can be kind of pricey, but it is an excellent program. There are things like MathCAD, which are a lot more cost-effective and they work well. Or there's even a program called Maxima, which is kind of an open source program. It's a little more awkward, but it's a symbolic program as well. Okay? I'm sure there are probably other ones too.